HABER'S.com.
Okay, now we are going to study commercially important topic, HABER'S process. Okay, it is important for board exams also, and every exam there will be definitely one question from the HABER'S process. The problem is it is interlinked with the Lee-Chatler principle, and reasoning questions they are asking, not only the sequence. So because of that I am going to explain everything with the reasons. Okay. So HABER'S process is basically used for manufacture of ammonia, and raw material used are nitrogen and hydrogen. Okay. The main problem of this reaction is reversible. So whenever there is a reversible condition is there, we have to use the Lee-Chatler principle, so that more quantity of ammonia must be manufactured. Further, if you study this reaction carefully, then this total sequence will be very easy for you. See here, enthalpy of formation of ammonia is minus 46.1. So this value is not much important, but negative sign is more important. That means it is an exothermic reaction. And one more thing you will remember, here 4 moles on the left hand side, 2 moles on the right hand side, and all reactant and products are in the gaseous state. So accordingly we will select the pressure. Okay. So the moles are important for selecting the pressure, and formation sign will be important for the selection of the temperature. So let us take here N2 and H2 are compressed to a 20 megapascal. This is 10 to the power of 6 pascal. Okay. So why it is that much pressure is required? Just because this is a reversible reaction and we want to prepare more ammonia. So to keep the reaction in the forward direction, high pressure is required according to the Lee-Chatler principle. Lee-Chatler principle says that when pressure is increased, then the equilibrium will shift in the less number of moles side. Here 4 moles, here 2 moles, and we want that reaction must be in the forward direction. So to keep it in the forward direction, we have to apply more pressure. So when you apply the more pressure, automatically reaction will be favorable for more ammonia. So this 20 megapascal value also important. Why it is so much of pressure is, that is also important. Okay. Now after this is called as a preheater. This is called as a preheater in the catalytic chamber. So earlier days we used to use iron as a catalyst, molybdenum as a promoter, but nowadays it is not used. Nowadays iron oxide is a catalyst and promoter small amounts of Al2O3 and K2O. These are the two promoters required. Okay, so why we are using the preheater? Why not to use directly a high temperature? Because if we see, it is an exothermic reaction. Exothermic reaction is favorable at low temperature. But if we maintain the low temperature, the rate of reaction will be slow. So to improve the rate of reaction and without losing the yield, more ammonia, it should be heated in the preheater itself. Optimum temperature for maximum ammonia with minimum possible time is 700 Kelvin. So these three things, iron, molybdenum earlier, nowadays it is Al2O3 and K2O. So here N2H2 will come here and they will react with each other. So how to separate them? According to Lee-Chatler principle, when you decrease the concentration of product, then reaction will shift in the forward direction. So but how to separate? All are in gaseous state. Then we use a method of liquefaction. So once you carry out the liquefaction, ammonia will come out. Okay. But still it is a reversible reaction. 100% product will not be there. Some amount of N2, some amount of H2 will remain. So those hydrogen and nitrogen gases are pumped back by the pump. So this is a collecting. This will collect the extra nitrogen and hydrogen which could not form as ammonia. So when you remove this, then they will start in this direction. That again nitrogen and hydrogen will be pumped back and they will be passed. This reaction will keep on continue. This nitrogen and hydrogen will keep on continue. Okay. So the main things you will remember: compressor to reaction shift the equilibrium in the forward direction. 700 Kelvin because it is exothermic, so it should not be directly heated. And earlier iron and molybdenum, nowadays iron oxide and Al2O3. So this is separated by the liquefaction method. So that's all for the Haber process, how we prepare the ammonia by using the very cheapest element, nitrogen and hydrogen. I think you understood.